Hello everyone. Hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of GIS data input, projections and transformations. So basically the data input is the process of encoding the data into a computer readable format. Data input is the process of encoding the data into a computer readable format and writing it into a GIS database and writing it into a GIS database. So for civil engineer, this data comes from various sources like traditional survey or advanced total station surveys, GPS coordinates, scan blueprints or satellite imagery. This stage is often the most time consuming part of a GIS project, sometimes accounting for up to 80% of the total effort. So quality control is the paramount because special errors introduced during that input will propagate through all subsequent engineering analysis, leading to inaccurate quantity estimates or site layouts. So the data storage and data retrieval, there are two main terminologies are most important for the civil engineer point of view, where we have to retrieve the data and we have to store the data based on the collected information, which is a vector or raster. So GIS stores large volumes of spatial data in databases. The objective is efficient storage and quick retrieval. So we have to get the data quickly and we have to storage the data efficiently. It works using database management system. Data is organized in layers and tables just like raster or vector. Retrieval is done through queries and spatial analysis. So civil engineers use it for managing projects, data model or managing the project and land records department. So after storing and retrieving the data, we have to transform the data. So data transformation, which is one of the procedure where it converts the data into usable formats or projections. The objective is compatibility and accuracy in analysis. So we have to maintain the compatibility and accuracy in analysis by using that transformation phase. It works through coordinate transformation, projection and scaling. So which ensures the consistency across the data sets. Also, it includes that the raster vector conversion or the raster to vector conversion and vice versa. So important for civil engineer or in the projects which involves the multiple data sources at a time and they are work interdependently or interconnectedly. Data input refers to entering geographic and attribute data into GIS. So the main objective is to ensure the accurate and reliable data collection. It works through digitization, remote sensing, GPS and surveys. So characteristics includes that we have to maintain the precision, we have to use the data formats and we have to correct the source and its reliability. So data can be primary or secondary. Just like primary, we can collect data from field survey and the secondary or we can collect the data from existing maps. So these all type of data is used in civil engineering for topographic mapping and site analysis. So manual digitizing and automated scanning, there are two methods where we can bridge the gap in between the analog to digital divides. So they are the data input methods where both methods work together or both methods work separately for the civil engineer domain. Moving towards the main point, which is the concept of georeferencing. Georeferencing is the process of assigning real world coordinates to a digital image. I repeat, georeferencing is the process of assigning real world coordinates to a digital image or a legacy map. So we do this by identifying control points where both the image location and the real world coordinate are known. The software then performs a coordinate transformation which follows shifting, scaling, rotating the image to fit the target system. In civil engineering, this is how we overlay an old scan site survey or we can superimpose the old scan maps onto a new satellite map. So here Fixed points are represented by the circle and control points are represented by the plus sign. So straight line, dotted line, rubber sheeted boundary, and zigzag line is for original boundary. So with respect to that, we can check the displacement vectors, we can check the source mesh, we can check the targeted grid, and we can compare the control points, that is ground control points. So alignment, rubber sheeting, correction, mechanism, these are four main parameters for the georeferencing concept. Alignment is for anchoring digital data to a coordinate system, or we can assign the coordinate system to a digital data. Rubber sheeting is a non-linear stretching to fit control points. So we can assign non-linear stretching also to a fixed control points or ground control points. In the correction, we fixes the paper shrinkage and lens distortion. And mechanism or the process shows that known points are taken down, unknown areas are interpolated. So we can take unknown areas also for our consideration, so that we can mark the known points for that unknown areas with reference to that georeferencing. Next, georeferencing is based on the coordinate transformation, where relative versus absolute positioning is there. If the transformation is done poorly, you know, or your known design will be superimposed on a distorted base map, compromising the entire project integrity. So in civil engineering, your design is only as good as the spatial framework where it suits upon, or where it built upon. So today we will discuss how we bring data into the system, how we handle the mathematical flattening of the earth through map projections, and how we transform coordinates to ensure everything aligns perfectly. These steps are the behind the scenes. These steps are the behind the scenes work that ensures a pipeline design in the office ends up in the correct spot in the field. So we can plan everything in the office, but we have to execute the whole plan on site. So relative versus absolute positioning is most important point with respect to the digitizer units, just like the hardware, and with respect to the real world units that are based on the GIS. So we are working on the hardware in the office. We can mark the point, we can correct the points, we can locate the plan, we can mark the plan, everything. But on in the real world phenomenon, and in the real world scenario, based on that GIS, we have to transform that digitizer units in the real world application. So we have to bridging the gap between hardware device and geographic reality by using that transformation matrix. So transformation matrix plays an important role for the conversion of hardware data or the hard copy data on the real world units based on that GIS, where we can mark the projected location based on that raw input. Then most important point is the datum thing. Sometimes we must move data between different datums, just like mathematical model of the earth shape. So in India, we have the legacy data is based on the Everest datum, while modern GPS data uses WGS 84. Converting between them requires a complex 7 parameter transformation to account for shifts in the center of the earth and differences in the ellipsoid shape. So three shapes of earth are there: physical earth, geoid earth, ellipsoid earth. Physical earth is the irregular shape. Geoid earth, which is the equipotential gravity surface with reference to the mean sea level, and ellipsoid shape, which is the considered as a mathematical reference surface. So converting between them by using the civil engineering point of view, engineer working on the project with historical records failing to account for this datum shift can result in horizontal errors of several hundred meters, a catastrophic mistake for any site specific work. So with respect to the physical earth, to geoid, to ellipsoid, if we are civil engineer, we are working on the same, then we must get the error with reference to that georeferencing or the coordinate point of view. So basically datum concept is most important point for defining the shape of the earth, where the set of parameters linking the ellipsoid to the earth. So with respect to that, physical earth is treated as a geoid, is treated as a ellipsoid for the sake of our projections, our mathematical operations, or our ground control point marking. So that datum concept is most important point for the transformation phase. So for example, WGS 84, NAD 83, these are all the Everest datum or datums. With reference to that, we can take the reference for any geoid, equipotential gravity surface, or ellipsoid mathematical reference surface. Now, there are three coordinate systems. First is a geographic coordinate system, angular measurement on a 3D sphere. Angular measurement on a 3D sphere. So, it is a vital to distinguish between geographic coordinate system and projected coordinate system. So, geographic coordinate system, which is the angular measurement on a 3D sphere, and projected coordinate system, which is a converting 3D angles to a 2D planes. Converting 3D angles to 2D planes. So light source analogy is used in the projected coordinate system, but in geographic coordinate system there is a angular measurement. There is a angular measurement. So a ground control points, or we can say that geographic coordinate system uses three-dimensional spherical surface of the earth, and it defines location using degrees of latitude and longitude. I repeat, a geographic coordinate system uses a three-dimensional spherical surface of the earth and defines locations using degrees of latitude and longitude, where projected coordinate system is a flat two-dimensional surface. A projected coordinate system is a flat two-dimensional surface that uses linear units like meters or feet for x and y coordinates. So while we collect the geographic positioning system data in geographic coordinate system with reference to the WGS 84 datum, we almost always perform engineering design and area calculation in projected coordinate system. So we can use the projected coordinate system for the reference with reference to that datum. So mixing of these two without proper transformation is one of the most common causes of data misalignment in GIS. So with reference to that GIS point of view, if we are performing the activity based on GIS, we have to follow geographic coordinate system or projected coordinate system. Geographic coordinate system for the 3D sphere consideration, projected coordinate system for 2D planes. So we have to convert the whole earth, or we have to consider whole earth as a 2D plane. Otherwise, we 100% make mistake by taking the coordinate system, and that coordinate must be correct, so that our planning must have to be executed on real world scenario or on site is 100% correct. Otherwise, there will be a mistake for the ground control points. Third one is the Universal Transverse Mercator, UTM. In India or in much of the world, the Universal Transverse Mercator system is widely used for regional engineering projects because it perceives local shapes and angles exactly. For highly localized projects in the United States, engineers use the state plane coordinate system. In United States, engineers use state plane coordinate system for even higher precision. The goal is to select a projection that minimizes distortion or error within your project specific geographic zone. So understanding the projection properties of your GIS workspace is the first step to ensure that your measured lengths on the map must have to be equal the actual length on the ground. So map length and ground length we have to finalize based on that global engineering standard. So here cylindrical scant projection of the earth where 60 zones are there having 6 degree wide. Unit is meters used by 100 plus countries. And another is the central equator is there, northing and southing. So central meridian which gives the false easting 500 meter. So based on that system status, Universal Transverse Mercator active which gives the unit in meter, and origin is easting and northing with reference to that easting and northing. So this is a more precise coordinate system which is globally used, and in United States also precisely used for each and every project. What are the civil engineering applications for that coordinate systems? So coordinate systems in civil engineering must have to be accurate. So accurate coordinate systems such as geographic coordinate system, projected coordinate system, universal transverse Mercator are essential for converting real world locations into precise engineering data. So with reference to the highway design applications, cutting and filling calculations or the volume of cutting and volume of filling calculations, alignment design, infrastructural layout dependent on the accurate datums and projected coordinate system to minimize positional errors. So with reference to the watershed and terrain analysis or in the hydrology point of view, hydrological modeling and elevation analysis require consistent x, y, z coordinates in system like universal transverse Mercator for reliable flow direction, drainage, sedimentation and terrain interpretation. Based on the urban planning point of view or cadastral mapping, projected coordinate system and universal transverse Mercator reduce map distortion, which improves property boundary mapping, land subdivision and urban infrastructure planning accuracy. So moving towards the integration point of view, GPS and remote sensing integration, GIS integrates global positioning system field survey data with satellite imagery using common coordinate reference systems, which ensures accuracy, overlay, spatial analysis, and engineering decision making. At the end, summary, the data journey, which gives the physical earth to digital precision, where data journey from physical earth to digital precision. So this is a cyclic procedure where primary data input, secondary data input, map projection plays a crucial role or interconnected role. Now primary data input are the direct correction or the data collection, secondary data input which is the digitization and scanning point of view, and concept of map projection. We will see one by one. Primary data input, analog to digital. So primary data input involves collecting information directly from the source, specifically from the GIS project. This data is born digital and usually contains high spatial accuracy. So for modern infrastructure projects, primary data input is the gold standard as it bypasses the errors associated with manually converting old paper models. It provides the absolute truth coordinates that from the backbone of a site specific GIS data. So input is the analog to digital. So we have to collect the digital data only, or we have to convert the physical earth data to the digital precision, so that that input must be more reliable for the secondary application or procedure of digitization and scanning. So secondary data input refers to the use of existing data such as converting older paper based on as built drawings or legacy maps into a digital format. This is typically done through scanning and digitizing, where scanning creating a raster followed by digitizing tracing the features to create vectors. So means scanning is the process where we can create a raster, and digitizing is the process where we can trace the features to create vectors. So in civil engineering point of view, we often use to digitize old utility maps to understand existing underground networks before a new excavation starts. So before excavation, we can take the follow by using that scanning and digitizing activity based on that GIS data. While convenient, these secondary sources must be carefully georeferenced to ensure they match the correct projections or they match ground control points based on the projected coordinate system and precision requirements. Next to that process, map projection. So the earth is an irregularly shaped ellipsoid, but our maps and CAD drawings screens or assume it as a flat surface, that is just like a 2D plane. So map projection is the mathematical formula used to transform the 3D surface of the earth into a 2D plane. No projection is perfect. No projection is perfect. They all cause some degree of distortion in area calculation, shape calculation, distance measurement or direction. So not a single projection is perfect. They have a minute errors or distortion in between them. So for civil engineer point of view, choosing the right projection is a high stakes decision. Choosing the right position or choosing the right projection, which is a high stakes decision. So if you or we are using a projection that distorts distance for a multi-kilometer highway project, your material calculation and alignment curves will be mathematically incorrect. So based on that highway, just like example of highway, if we take a small projection distortion in a multi-kilometer highway, then your project required a large amount of material calculation and alignment curves, which will be mathematically incorrect. So we have to be precise. We have to be convert the physical earth to digital precision based on that data which is collected, where GIS helps us for the scanning point of view, for the projection point of view, or for the georeferencing point of view. Stay tuned, guys. Happy learning.